Hello, welcome to Statistical Methods. Welcome to this last video in the series. In this video I will be discussing variable selection and prediction in linear models. If you'd like to study this yourself, then head to chapter 19. So obviously variable selection and prediction is a very large topic in linear models. And there's even still ongoing research in this area, so in this video I will just touch the surface what's possible, and if you're interested to learn more about this, then you should attend further courses on linear regression models and of course also generalized linear regression models and other statistical models. So when I started this, I said we have several aims in regression. One aim is to find the regression model and determine how well it fits to the data, and then of course we also would like to make predictions, because with every statistical model we would like predictions. And this leads us to the idea of prediction intervals. So prediction, because so far what I've shown you basically is we have a training data set, and this training data set consisted of, we had X train and Y train, and we used this to estimate our predictor, which was basically estimate beta naught and beta, or more generally estimate our regression function f. And then now we have test data, and with this test data we can just plug in f x test, and then we get our y hat of x test, and this is a point estimate, so we get a label, so we predict a label, predict response or label, and this is necessarily just a point estimate. But we also are keen to estimate not just the point estimate, but we would like to estimate the interval, so a likely interval. So let's say this is our fitted f hat, so this is the fitted regression curve, that we fitted using training data. And now, so all of these are y hats for x, and ideally we would like to get some sort of confidence interval around the prediction. So we like to have a confidence interval for ci around the prediction y hat. And the question is, how do we do this? And it's relatively easy. So we know that the predictor, so this y star, is simply just the conditioned, the y conditioned on this. This would be beta naught plus beta transpose x. So this is our predictor part. And the variance of epsilon, so was the variance of y given x, so that was sigma squared y 1 minus omega squared. So the variance of that's basically the noise variance. And this means that the simplest way, so a very simple way, would be simply to use this error epsilon to create an interval around this. So a simple prediction interval is given by, let's say, y star x test plus minus some critical value times the standard error of epsilon. So this looks like, so if, for example, if epsilon follows a normal distribution, then we could use C 1.96 for 95% coverage. So the question is this a good interval or not? And the truth is that it's actually not going to be a good interval, because this ignores that we are actually estimating the predictors. So this prediction, so this will be an underestimate, as this only accounts for the irreducible error epsilon, but not for the error in f hat, that is in the error of the regression coefficients beta naught or beta. So so we have two factors, so we have two sources of noise in our prediction. So we have the generic intrinsic error, and then we have the error that comes from estimation. And so while we can use this above thing here, so we can use the predicted mean plus minus the residual error, this is just a crude approximation unless n is very large. So unless, so above predictor works for n large only. So there are formulas to describe better prediction intervals, but we will not be discussing those in this course, because they are actually quite a bit more complicated than this above, and also the underlying principle doesn't change. So the key idea is, if you really would like to have a more accurate prediction interval, you need to take account of the propagation of error from the error in the beta naught to the predicted error. So details will be in later regression modules. Okay, so that's about the prediction. So prediction is in principle possible, and you can do it in a naive way, and that usually is okay, but you should also, this doesn't take into account of the error of the regression coefficients. So now the next thing is variable importance. So in prediction, we like to find out which variable contributes. And contributes to both fitting the model and for predicting the model. So, because in statistics we have two aims. We would like to explain the data that we see, and we would like to predict data that we haven't seen. So let's recall again the variable decomposition. So with the variance of y is the unexplained variance, which was the variance of y times omega squared. So explained, I mean, so that's the explained variance plus the unexplained 1 minus omega squared. So this would be var epsilon, and this is var y star. And the question is so one way to answer variable importance is basically which predictors play an important role in omega squared. Because the larger, so omega squared is yx rho xx minus 1 rho xy, and basically what we're trying to measure is we have a measure that is a compound measure of the correlation between all the x and y, and we would like to dissect the multiple correlation into different parts. So dissect multiple correlation into the contributions of individual elements. And it turns out, so we've seen this before, so if the predictors are not correlated, then we can write omega squared is the sum over the individual, so the total squared, the total squared correlation is the sum of the individual squared correlations, namely the rho y xi squared So this means a predictor is more important the higher the correlation between the response, the more important the predictor is in explaining the data. So is more important the higher core xi y, and this is called the so-called marginal correlation. So one way to rank predictors would be to rank by marginal correlation. And in fact, that's actually turns out to be not a really bad strategy, because for high dimensions, for instance, when you have many variables, it often is the case that there are many predictors, but they are because of the high dimensional space, there's actually not much correlation going on. So the assumption of that most of the predictors are actually not very strongly correlated is actually given or satisfied. Obviously, there are other cases where this is not true. For instance, when you do spectral analysis, you have a lot of correlated things going on. But rank by marginal correlation is usually what you should be trying first. So that's simple, but often very effective. So what other criteria are available? So the most simple is the marginal correlation or squared marginal correlation. So marginal correlation squared. What other let's talk about which other criteria are there that you shouldn't use. So in contrast, what you shouldn't use is regression coefficients directly, because regression coefficients, they only give you the change of the response when you keep all the variables fixed. And so it's basically the partial derivative of the slope of the regression function, and they also incorporate the scale. So because they incorporate the scale, they are not suitable for determining the relative variance. For instance, when you change the units, you don't want to have, so when you change the units, then the regression coefficients will change, and of course changing the units will not make the variable more or less important. It's just that the units have changed. So it's basically regression coefficients are not scale invariant. So they are ruled out as a test or as a means for ranking. So not good for relative comparisons. So there are so-called standardized regression coefficients that fare a little bit better, but they are also closely related to marginal correlation. So you might as well just use marginal correlation. So there's one major contender for variable selection. That is more widely used than marginal correlation, and this is the so-called regression t-scores, and they are in fact linked to partial correlation, and this is what I will explain now. So regression t-scores, and these regression t-scores, they are actually taking into account of the scale of the variables. So regression t-scores, so what you do, you estimate your regression coefficient. So you estimate beta. For instance, you get beta hat, and let's say let's say we have beta 3, and then we estimate beta 3, and then we estimate the variance of beta 3, beta hat 3, and this we call variance hat of beta hat 3, and then we form a statistic, and this is our regression t-score. So we build the ratio of the fitted regression coefficients divided by the standard error of the regression coefficient. So this will take care of the scale, and it will also at the same time include the uncertainty about the fitted regression coefficient. So if our aim, so if you recall when we did the maximum likelihood estimation, the fitted regression coefficients, they have a distribution around the mean, and they're typically normally distributed, and we can use this distribution to test whether we want to, whether they're zero or not. So this is basically the test statistics, like the Waltz test statistic for the test that because if you recall, in the Waltz test statistic, we subtract the value that we're testing, and if we test whether it's zero, then this would be our test statistic. So this is the test statistics, whether the regression coefficient is zero, and if this is large, then we can reject the notion that this is zero. So this is why this is important. And this regression t-score is also listed in the R output. So excuse me. So let's call this not 3 but I. So this is for Ti. So we know that Ti is roughly asymptotically normal distributed with so because it's basically a Waltz type statistic. For true testing that is zero, so it's under beta I equals 0, it's normal distributed around 0, so n01, and that's the asymptotic distribution, and the exact distribution is actually the t distribution with degree of freedom n minus d minus 1 under exact for normal data. So if everything is normal, then you can show that while it's asymptotically n01, it's for finite n, it's t distributed with n minus d minus 1. So these are so this is the distribution of the regression t-score. And we can use this to compute a p-value. And then we can conduct a statistical test and reject whether the try to reject that this regression coefficient is 0. So try to reject that coefficient is 0. So that's how this regression coefficient works. So of course we can also use the regression coefficients to rank the predictors. And if we do this in R, you will get the following output. So the R output, and you'll do this in one of the worksheets, the R output will consist of the regression coefficients beta hat I, then it will give you actually the estimated error of the beta hat I, then it will give you the regression t-score as the ratio of beta hat I divided by the SD beta hat I, then it will give you p-values based on t distribution, and then it will also indicate the level of significance. So normally, so if it's 1 star, 2 star, or 3 star, and 2 star if it's basically 95%, 99 if it's 3 star, and 90% if it's 1 star. So if you use LM, you get all of this by hand. In the worksheet, in one of the worksheets, you will be aiming to reproduce the output of LM by programming it yourself. So the intriguing thing is that there is a connection between the partial correlation and the regression t-score. So connection between partial correlation and regression t-scores, and it turns out that they're actually doing exactly the same. So partial correlation is when you have the correlation of y given between y and given xi, and then you keep everything else constant, or you condition on them basically on all j that are not I, and it turns out that this can be, so this partial correlation is actually the regression t-score divided by the t-score squared plus the degree of freedom, and the degree of freedom is n minus d minus 1. So whenever you compute a regression t-score, you actually compute a partial correlation. So ranking by t-scores is the same as ranking by partial correlation. So basically what I'm recommending here is to use either marginal correlation or partial correlation, and both will give you slightly different insights in what's going on. So the marginal correlation will actually give you insight which predictor is allowing to fit the actual data, whereas the partial correlation will be allowing you to test whether a predictor is 0 or not. So these are the two main things that you will normally use in linear models. And if you look into the literature, there are a lot of other approaches that have been discussed in terms of variable selection and variable ranking, and in fact there's a plethora of methods, and many of them will be related to stochastic search. So other methods, and so what I said, many will be related to stochastic search, because it's clear that there is not a single set of models, linear models, that can be often. Sometimes there is a single best model, but especially in high dimensions, so high dimensional variable selection is tricky. Difficult because of the non-uniqueness of the sets of important variables. Existence of multiple equally good set of predictors. So I mentioned several times that in machine learning often the emphasis is on predicting and not much on explaining. So if your aim is to explain things, then of course you would like to find predictors that explain your outcome. If you are more on the side of you just want to predict, then of course you are in a less demanding position, because you just want to predict, and then you can basically work with any set of predictors that produce a reasonable result. So that's one thing. So we have high dimensional variable selection, and we have these multiple sets of equal predictors, and then of course we also have non-linearities. And these non-linearities, they also pose a little bit of a problem, because even while I said that there's often not much correlation in high dimensions, there can still be non-linear relationships, and that we need to go beyond the linear model. And going beyond the linear model, so I mentioned many times in this course, and I actually started with this course, with entropy and relative entropy. So one way to overcome this is using entropy-based models and methods. And one generalization of correlation, so for instance, you can generalize correlation, and then it becomes something called mutual information. So we'll discuss this in more detail also in the multivariate course. But there are ways to generalize dependence measures to include nonlinear effects and other non-normal distributions. So if you'd like to learn more about this, then I can suggest very warmly to you to subscribe to the multivariate statistics module in year 3. That's where you'll learn about these things. So in short, so what a lot of people are doing in settings that are not fitting into a linear model very well is to use entropy-based methods, in particular based on mutual information, to select variables that are good for predicting and also good for fitting the model at the present data. But for the case that we've been considering here in this class, in the simple linear model with normal error, the two key methods are simply the marginal correlation, so the correlation between each predictor and each response separately, and the regression t-scores, which in turn actually take account of the other variables, because because of the link with the partial correlation, it actually means that you condition on the other variables when you look at the regression t-scores. So that's it with this course. So I hope you enjoyed the course. I hope you learned a lot. So we talked about likelihood, we talked about Bayes, and we talked about linear models. And even if you wouldn't do any further statistics class, you should be pleased to know that if you know likelihood and if you know linear models, you can probably solve 95 or 90 to 95% of all problems out there can be solved with these simple, or it's not simple, but with this still elementary set of tools. So hopefully this course has helped to understand these tools a little bit better. And whatever you're doing in your next step, I hope that you will be able to successfully, not just only to successfully apply, but also to successfully understand what's going on. In this sense, I hope I'll see some of you in my course in year 3 in multiple statistics, and otherwise I wish you all the best for your future exploration of statistical methods. So see you and bye bye.